My name is Mike Jones from Mitsubishi Electric Research Labs, aka MERL, and I'm going to talk about joint work with Bharathkumar Ramachandra from NC State. The paper is entitled Street Scene, a New Data Set and Evaluation Protocol for Video Anomaly Detection. This work has three main points. First, we present a new data set for single scene video anomaly detection. Second, we present two new evaluation criteria and point out flaws in the commonly used criteria. Third, we present a novel baseline algorithm for video anomaly detection and show results of the new algorithm on street scene as well as comparing against past approaches. Currently, publicly available data sets for single scene video anomaly detection, such as UCSD PED1 and PED2 and CUHK Avenue, are relatively small and they don't contain much variation in normal activity. Normal video consists mostly of people walking. Our new street scene data set is much larger, has much more varied normal activity, and has a much greater number of and types of anomalous activities. The normal video shows a street scene with 2 lanes of cars, 2 bike lanes, 2 rows of parked cars, 2 sidewalks with pedestrians. This slide shows examples from the normal activity from the data set. Here are some characteristics of this street scene data set compared to other video anomaly detection data sets. Street scene is significantly larger in terms of number of training frames and testing frames. It has almost as many anomalies as all the other data sets combined and has many more different anomaly types. Here are some examples of labeled anomalies. If you can see them, illegal U-turn, jaywalking, a meter maid placing a parking ticket, a motorcycle driving on the sidewalk, a biker outside a bike lane, and a biker on the sidewalk. In addition to the new data set, we also introduced 2 new evaluation criteria that do a better job of evaluating how well a video anomaly detection algorithm can be expected to perform in practice. Our region-based and track-based criteria both determine correct detections by calculating the intersection over union ratio between detected regions and ground truth anomalous regions. False positives are counted for any detected regions that do not overlap significantly with ground truth anomalous regions. These criteria fix the serious flaws of the standards frame level and pixel level criteria that are in common usage. For example, in this frame on the left, the red shaded region represents the set of pixels detected as anomalous by some algorithm, and the blue bounding box represents the ground truth anomalous region. The red shaded region is obviously not localizing the anomaly well. Our new criteria would correctly count this as 1 misdetection and 1 false positive. The old frame level and pixel level criteria would count this as 1 correct detection. In this next frame, where the anomalous jaywalker is not detected, our new criteria would correctly count this as 1 misdetection and 2 false positives, while the old frame level criteria would count this as 1 correct detection, and the old pixel level criteria would count this as 1 misdetection and 0 false positives. Finally, we also present a novel baseline algorithm and show results for some variations of it on street scene. We compare with a previously published dictionary-based method and autoencoder-based method. Please come to our poster for more details.
Good afternoon, everyone. I'm Prabhat Kumar from the Indian Institute of Science and will present our work detecting face-to-face facial reenactment in videos. Deepfakes are fakes generated commonly by deep neural networks. These fakes depict manipulation in physical characteristics of a subject or the target in some aspects, identity swap in the case of face swap, and action swap in case of reenactment. Reenactment is a type of deepfake. Reenactment refers to alterations done to actions performed by the target in the video by the actions of a source while keeping the identity of the target intact in the altered media. These alteration in actions can be in form of change of facial expressions, mouth movements, and in some cases, body movements. We aim to detect such manipulation on a frame level basis. Through our paper, we propose a multi-stream network for detection of facial reenactment by face-to-face. Sorry for the typo. We also propose a loss function for the balanced training of various streams of the proposed architecture. The proposed pipeline is as follows. Given an RGB video, we sample RGB frames, followed by face detection and extraction. The extracted face is then divided into a 2x2 grid, and it's fed into the network along with the full-phased image. The proposed multi-stream network based on a 2-level spatial pyramid structure consists of 5 parallel ResNet 18 models, where ResNet 2 to 5 are known as regional classifiers, which are dedicated of learning local regional artifacts left behind by the face-to-face, whereas the ResNet 1 learns the most discriminant features across the face in general. The scores from these 5 parallel ResNets are then concatenated to form a 10-dimensional score vector, which are later fused to form the resultant 2-dimensional vector corresponding to the 2 classes, original and altered. The proposed The proposed model is then trained end-to-end by the given loss function. The loss function primarily consists of three terms: the full phase loss, the regional loss, and the fusion loss. The full phase loss corresponds to the cross entropy loss of the full phase routine. Similarly, the regional loss is defined as the summation of cross entropy loss of the regional classifiers. This is done to avoid the partial training of these regional classifiers. The fusion loss is calculated at the final output of the network and is parameterized by the factor lambda. We report the results of our proposed method on the phase forensic dataset as per the experimental protocol defined for the dataset. We observed that the proposed model gives better or at par results with the present state-of-the-art detection methods for the three compression modes. For more details can be found at our poster. Thank you.
Hello again, sorry. I'm Mike Jones from MERL again, and I'm going to talk about another paper on video anomaly detection titled Learning a Distance Function with a Siamese Network to Localize Anomalies in Videos. This is joint work with Bharathkumar Ramachandra again and his advisor Ranga Vatsavai, both from NC State. So the problem of video anomaly detection is to localize, both spatially and temporally, unusual activity and testing video of a scene for which you're given training video containing only normal activity. So we are interested in the single scene version of this problem because it corresponds to the most common use case. In this version, anomalies are location specific, i.e. what is anomalous in one region of the scene may not be anomalous in another region. In this example from the UCSD PED1 dataset, non-pedestrian objects on the pedestrian walkway are anomalous, and so would be a pedestrian walking in the grass, for example. The basic idea of our approach is to learn a distance function between pairs of video patches. So a video patch is a spatiotemporal volume of the video. If a test video patch has large distance to all training video patches from the same region, then it is anomalous. So instead of storing all training video patches for each region, we store a set of exemplar video patches that cover the range of different activities in each region. So the main problem of our approach is what the distance function should be, the distance function between video patches. So we learn a distance function in the form of a Siamese convolutional network that takes two video patches as input and outputs a distance. The network is trained on video patch pairs from auxiliary video that is not specific to the target testing dataset. Video patches are represented by a raw image region along with the corresponding flow fields from 6 consecutive frames. Our network applies a number of convolutional layers to each video patch and then uses the absolute difference of the resulting feature vectors, followed by more convolutional layers, to output a distance between 0, which stands for similar, and 1 being different. So we show results on the standard test sets, UCSD PED1, PED2, and CUHK Avenue, that are near or above the current state of the art. Here at the top, it's probably hard to see, but we see an example of an anomalous skateboarder being detected. And at the bottom, we see a detection of a person walking in an unusual direction. And then the next part is a person throwing a book bag in the air. These are all anomalies. In summary, we present a new metric learning paradigm for video anomaly detection. Our method is based on training a distance function, which can be done once offline and applied to many different target data sets. Finally, it uses a simple exemplar-based model of normal video that is fast to learn and very easy to extend. So please visit our poster for more details. Thank you.
From Hong Kong Baptist University. The paper I'm presenting is Temporal Similarity Analysis of Remote Photoplethysmography for Fast 3D Mask Face Presentation Attack Detection. This work is jointly done by Dr. Xiangyuan and Professor PongChi. Nowadays, people tend to post their face image online for different purposes, and these images can be easily used to spoof the face recognition system. Prints and screen attacks can be tackled by the appearance-based method, as they have similar artifacts. However, we are facing a new challenge with the development of 3D reconstruction and printing technology. The quality of the 3D masks can be so good like this, so that even humans can hardly identify them. In this case, the appearance-based method may not work. Recently, RPPG was introduced as a new liveness queue to tackle this problem. Here is the principle. Simply speaking, we can use a normal RGB camera to obtain the heartbeat-caused skin color variation. When apply this technology to our task, for genuine face, we can observe the heartbeat signal, while for masked face we cannot, since it is blocked by the mask. Some of the previous methods extract local RPG signals from small facial regions and use the spectrum analysis to form the final liveness feature. This method requires relatively long observation time to observe a differentiable spectrum pattern. This is not convenient in real application, since nobody likes to wait such a long time to access the security system. Therefore, we propose Temporal Similarity Analysis Approach, TSR-PPG, in this work. From the observation, we can find that the amplitude cannot be directly used as the liveness feature, since it varies at different phases for different subjects. So we propose the TSR-PPG operator, which calculates the distance of every two local RPG signals in a cross-correlation manner. For genuine face, the minimum distance can be reached when the two signals are aligned, and it increases when sliding them away from each other. Such a pattern is different from masked face. We extract the features such as the mean or the standard deviation on it to form the final liveness feature. The proposed TSR-PPG not only can adapt the variation of amplitude and phase, but also can detect the detailed heartbeat variation. We also performed TSR-PPG on the gradient and phase of the local RPG signals, and the final result is obtained through the score-level fusion. Experiments on 4 datasets demonstrate the effectiveness of the proposed method. Thank you.
Welcome to the spotlight presentation of text-based person search via attribute-aided matching. This work was done at Indian Institute of Science, Bangalore. Text-based person search is an important problem in the field of intelligent video surveillance. The task is given a text description of the target person and a large gallery of images captured from multiple cameras. It is required to rank the images based on the relevance to the query. In this work, we hypothesize that incorporating attributes during feature learning shall help in the task of text-based person search. The reasons that support the use of attributes are as follows. Firstly, attributes have been shown to help learn fine-grained image features and be effective in image-based person search. Secondly, attributes are modality invariant and can help in bridging the modality gap between image and text. Thirdly, unlike class labels, attributes are universal concepts and are applicable even to unseen identities. Since attributes are unavailable in text-based person search, for each person ID in the training set, we extract the noun phrases from the corresponding text descriptions and use them as attributes as illustrated in the figure. In most conventional methods, a class-driven space is learned by using classification and triplet loss. In our method, we propose to utilize the attributes for improving the features by learning a novel attribute-driven space along with the class-driven space. The attribute space helps to rank the data points using semantic similarity, and finally, the retrieval is done using similarity scores from both the spaces. For the attribute space learning, an attribute classifier is introduced, and both image and text features are trained to ensure that the predicted labels match the mined ground truth labels. We further align the attribute space features based on semantic similarity by introducing a novel semantic triplet loss, which applies an adaptive margin onto the conventional triplet loss. We quantitatively establish our hypothesis by performing extensive experiments on benchmark dataset CHK-PEDIS and obtain substantial improvement over prior state-of-the-art works. We further observe that the model predicts appropriate attributes for unseen data points and hence provides even human interpretation for the examples. Thank you. For more details, you're welcome to our poster.
Good afternoon, my name is Royston, and today I'll be presenting our work on multi-timescale trajectory prediction for abnormal human activity detection. This is joint work with Neha Bragwa, Rajbabu Velmurugan, and Subhashish Chaudhary. Given a sequence of surveillance video frames, our aim is to detect abnormal activities. By that we mean temporal localization of anomalies. In the left, you see a group of people protesting in a pedestrian area. And at the right, what we expect from the system is a plot of anomaly score versus frame numbers. Anomalies occur at multiple timescales. Limiting one's analysis to a particular timescale will help detect anomalies only at that timescale. In the left, you can see a offense. It's a short-term anomaly, and on the right is an example of a person loitering. Such an anomaly is long-term in nature. We pose the problem as a human trajectory prediction problem. We do it at multiple timescales. We make use of 1D convolution modeling, human pose variation as a function of time. Future pose trajectories for each timescale act as ground truth for intermediate layers of our model. Here are some results. On the right side, in orange, is the input trajectories to our model, and in yellow is our prediction. Below in green, we overlay the actual future trajectories over the predicted ones. Our model is able to learn pedestrian motion and is able to predict trajectories corresponding to normal activities accurately. Here is another example. In this example, cycling in a pedestrian area is considered anomalous. Our model generates large deviations for abnormal samples. Since the model has been trained only on pedestrian trajectories, it extrapolates the future as pedestrian motion. Now we show the advantage of multi-timescale framework. In the loitering case, long-term trajectory prediction leads to large deviation in the prediction error. For such an example, operating at a smaller time scale and predicting shorter trajectories does not produce large deviation. This is evident from the plot shown below. We release a new large-scale single-camera dataset for anomaly detection. We call it the IITB corridor dataset. It contains single person as well as group of people. We report frame-level AOC. We achieve state-of-the-art results on 4 datasets. Thank you, and please visit our poster.
Good afternoon, everyone. My name is Shivangi Yadav, and I'm a PhD student at Michigan State University. And my research topic is relativistic discriminator, a one-class classifier for generalized iris presentation attack detection. And before moving on to proposed algorithm, let's go over some important terms that I'll be using pretty frequently in this presentation. So presentation attack refers to physical artifacts such as cosmetic contact lens, printed eyes, artificial eyes, and Kindle display attack. And presentation attack detection refers to algorithm that aims to distinguish between these two classes. These algorithms are typically binary classifiers that are trained on both the classes. For example, in a simple binary classifier, decision boundary is learned over training data set with known PAs. However, if the test set contains PAs that were not present in the training data, then these classifiers fail to detect them. For example, in this histogram shows the performance of current iris pad algorithm for seen and unseen PA scenario. And as you can see that these algorithms fail to perform in unseen scenarios. For example, the performance of TL pad decreases from 93.36 to 4.75 for unseen cosmetic contact lens and Kindle display. We aim to solve this problem using motivation from anomaly detection problems where approximate distribution of class of interest is learned and anything that lies outside this distribution are rejected. In our proposed algorithm, we aim to utilize trained relativistic discriminator from RASCAN as a one-class classifier. So this algorithm has been divided into 2 parts. First, train the RASCAN to generate good quality data that challenges discriminator, and then use the trained discriminator as one-class classifier for unseen PA detection. But how does this work, and especially like a one-class classifier? So relativistic discriminator is trained on bona fide and synthetic data that closely resembles real iris. This helps discriminator to learn tight boundary around the class of interest, and anything that lies outside this is classified as PAs. But the problem here is that it learns a very tight boundary around the bona fide sample because of the resemblance that leads to high error rate on bona fide class. To overcome this, we propose to modify relativistic discriminator by fine-tuning it with some more bona fide samples and very few PA samples. And as you can see from the results in the given histogram, our proposed method 1 and method 2 performs better than current algorithm for unseen scenarios. So to summarize, we proposed a new method for generalized iris presentation attack detection, and experiments were done for both seen and unseen scenarios. And as you can see from our results, the proposed method performed better than current iris pad algorithms. This proposed methods can be expanded to other biometric modalities as well, such as fingerprint and face. And thank you, and please visit our poster for more questions.
Hello, my name is Paul Marchwika, and today I'll be presenting unsupervised domain adaptation in person re-ID via K-reciprocal clustering and large-scale heterogeneous environment synthesis, which I prepared along with my colleagues Devinder Kumar, Prathapan Siva, and Alexander Wong. To start, person re-identification is the problem of matching images of individuals across non-overlapping camera views among a gallery of others. An individual can vary greatly between images on account of changes such as pose and background. If we want to deploy a re-ID system in a new environment, we generally have a few approaches available. Supervised learning, which relies on annotated labels from the target domain, which may be costly or difficult to obtain. Direct transfer, which uses a network trained on a separate source domain directly, but can be limited by the robustness in the source domain. Finally, unsupervised domain adaptation, which is fine-tuning a network from another domain using unlabeled data from the target domain, which can be limited in its ability to convert the embedding space from source to target. Improving the limitations in the latter two approaches is our main focus. Our proposed solutions are, 1, using K-reciprocal re-ranking during unsupervised learning to generate pseudo-labels for the target domain, a process which we call KT-CUDA, and 2, synthesizing a robust source domain to handle a wide range of image variation, which we call SHRED. For our KT-CUDA approach, we define a K-reciprocal distance for use in clustering tracklets. Instead of using raw distances, we find which tracklets are Kth nearest neighbors of each other, then we use our maximum K as the distance. The entire KT-CUDA process is an iterative learning algorithm. We start with initial weights from a separate source domain and generate tracklet embeddings in our target domain. We form a graph where each edge is the K-reciprocal distance between two tracklets, and then threshold these distances to form a cluster graph. These clusters are then used as unsupervised labels to fine-tune the network for a specified number of iterations. SHRED, our multi-source image domain, is composed of a number of well-known re-ID datasets shown here, and excludes any single camera identities. Variations of SHRED were produced to exclude any dataset under test. Using only SHRED in direct transfer tests, we get state-of-the-art performance in mean average precision on Mars, beating even results that use unsupervised learning. We also get state-of-the-art results on Market 1501. Using both SHRED and KT-CUDA combined, we get state-of-the-art performance MAP on several test datasets and best overall average performance. For a more complete set of results, please stop by during the poster session. Thank you.
Hi, my name is Neeraj Matkali, and I'm here today to present my work titled Video Person Re-Identification Using Learned Clip Similarity Aggregation. So, in video-based person re-identification, the goal is to match persons in videos captured from multiple non-overlapping cameras. Given a query video and a set of gallery videos, the re-ID algorithms compute a ranked list of the gallery videos so that the videos containing the same persons as the query rank higher in the list. In our approach, we split input videos into short clips and estimate the video level similarity as a weighted aggregation of clip level similarities of the clip pairs. The idea is to filter out non-informative clip pairs by giving them low importance scores. The non-informative clip pairs include the ones with dissimilar pose or with heavy occlusion. Our model samples clip pairs in a sequence, combines them using element-wise dot product, and assigns them an importance score, and then pulls them into a video feature vector. Once all clip pairs have been processed, the final video similarity is computed as the sum of elements of the pooled video feature vector. We use top T% aggregation, also known as competitive aggregation, as the baseline in our experiments. It takes top T% of the clip pairs with the highest similarity and averages those similarities to estimate the final overall video level similarity between the two videos. We evaluate our method and the baseline at different levels of input clip corruption. We simulate the clip corruption using JPEG compression, and our results show that our method is significantly more robust than the top T% aggregation baseline. Especially at high rates of input clip corruption, we perform much better than the baseline. Here we show 3 examples of pairs of query and gallery videos. We visualize the 2 lowest scoring clip pairs for each example, and we can see here that heavy occlusion or a person missing from the frame in one of the clips, or different persons in different frames due to tracking error are some of the reasons for low scoring clip pairs. For more details, please visit us at our poster. Thank you.
Hi, my name is Sobhan. I'm going to talk about a smoothful and efficient framework for computing smooth adversarial perturbations. This work is done at West Virginia University. So, adversarial examples are examples that are made using very small perturbations, which are perceptually indistinguishable, but at the same time they can fool the classifier. So for instance, as you can see in the images, you can have a panda and that just add a small perturbation. I'm gonna change the class. So what we're gonna do, we're gonna present a very smooth adversarial perturbation, and this is gonna be very significant because it's when you, for instance, when you print something, the smooth adversarial example is going to work better. It's robust to more attacks, and it's more transferable. So what we do, we adapt the deep fool framework, but what we do is we find the point on the boundary using deep fool, then we smooth the perturbation, and we repeat this procedure till we find a very smooth perturbation on the boundary, for which the adversarial example is on the boundary. So here we have some results on ImageNet, Cypher10, and MNIST. So as you can see, when we increase the sigma, which means when we increase the smoothness, we have a smoother and smoother perturbations, but at the same time, the image is visually indistinguishable and the class has changed. Then we have the performance versus the smoothness, and finally we have the comparison with the other models. We have the transferability, we have the per class success rate, and finally we have some universal adversarial examples using the smooth perturbation. And for more discussions, please stop by the poster. Thanks.
Hi, my name is Eric Ranger. Person identification, as you know, is an important task in many surveillance applications or computer vision tasks. It's a challenging task in real-world scenarios, in particular due to misalignment of people across camera viewpoints. So state-of-the-art techniques that deal with misalignment issues are mostly focused on feature aggregation, either by weighting, different forms of pooling, gated recurrent units. These are great techniques, but they tend to rely on complex architectures, and they also rely on late fusion of context information. And this does not allow us to leverage the information to do some training of the backbone network. So, our objective is, in this paper, is to propose a deep ReID model that can encode pose information. In particular, we propose a ReID model that does pose-gated fusion, so it incorporates a gating mechanism to select the best filters to address misalignment issues. It also allows for finer-grained learning of the informative appearance features. So here's the overall system. So at the top, you have the backbone network that provides appearance features. At the bottom, you have this pose net that provides context information on body parts and pose for the gating network. And then in yellow in the middle, you have the gated fusion net that combines appearance and pose features at the mid-level layer. So that's the context information. And then it provides aligned features to the rest of the backbone net. Okay. So here we have the gated fusion. So if you have appearance and pose features, it does two things. There's a squeezing net that aggregates appearance and pose and does spatial attention, or learns spatial attention. Then you have the bottom part, the nonlinear excitation that does channel-wise attention learning. If you come to the poster, I can show you some interesting results. Here you have examples of 6 people across 2 cameras of market, and here you have the image, the pose map, and the corresponding areas produced by gated fusion. We also have good results with market when we integrate gated fusion into TriNet, which is considered to be a weak baseline. We also produced the same kind of results with other data sets. Here we have Duke and Kook3. We also have positive results with PCB and BOT, so those are stronger baselines. And finally, we confirm that gated fusion consistently performs better when we apply it at the mid-level layer. So thank you for your attention.
Good afternoon. My name is Michael King. I'm from the Florida Institute of Technology. I'm here today to present the work of our friends and colleagues at the University of Houston. Unfortunately, they could not make the trip to be with us here today, and they send their apologies. This paper introduces a new cross-spectral data set that can be used in addressing the problems of pedestrian detection, face detection, and face recognition, and the data set is named EDGE-2O. EDGE-2O consists of images captured in open spaces during the day and night scenarios using both visible and near-infrared spectra. The data set provides rich sets of annotations to support the evaluation of pedestrian detection, face recognitions in different settings. The annotations provided by EDGE-2O consist of subject IDs, person bounding boxes, face bounding boxes, and face labels that indicate face pose, including frontal, profile, and back. The 2 human annotators were involved in the task of image annotation. EDGE-2O contains nearly 3,500 images captured from 197 subjects. Even though EDGE-2O contains a relatively small number of images compared to other data sets, it is very challenging due to the unconstrained acquisition conditions. The authors have established several baselines on pedestrian detection, face detection, and face recognition. These baseline algorithms allow them to identify the challenges of EDGE-2O in these problems. For example, in pedestrian detection, one can notice the challenges of cross-spectral matching, motion blur, and low-resolution images. While in face detection, the challenges include large face pose, and occlusions. Specifically, for face recognition, S2O contains multiple types of challenges, including cross-spectral matching, motion blur, low-resolution images, large face pose variations, and occlusions. If you're interested in learning more about how the data was acquired and the performance on state-of-the-art algorithms, please stop by and see poster 38.
Good afternoon. My name is Babu, and I'm presenting the work on fingerprint detection by my colleagues Anusha, Sayan, and Subhashish Chaudhary from IIT Bombay. So to do this, we first need to know what is fingerprint spoof detection. So if given two fingerprint images, it's difficult humanly to distinguish between a live fingerprint versus a fake or spoofed fingerprint. The objective in this work is to detect such fake or spoofed fingerprints which could be obtained because of sensors or some material on top of a regular fingerprint. For example, if you have an automatic fingerprint identification system which could identify a person based on its fingerprint, if he uses a spoofed fingerprint, then the security in such a system is compromised because he has tried to breach the system. So to handle this, they proposed a network called as the defraud net, which helps identifying spoofed fingerprints so that the security in the system is preserved. To do this security preservation, we will now look at the network which was proposed to identify such spoofing. So this network actually consists of the first stage where it takes the input image of a fingerprint. It does some pre-processing which is well established in fingerprint identification, such as local binary pattern extraction and Gabor filter extraction, which gives you edges. Then they form patches from these images so that these patches can be fine-tuned later. And in addition to extracting the features from these patches, they also extract features from this image, giving us some global features which help us identify the feature. From each patch, they use a channel attention to identify which of the features is important, and they also use a spatial attention mask which shows which aspect or which region of the fingerprint is more critical in detecting a spoof. Together, these are combined, these features are combined or pooled in a patch attention module, which is the proposed module. And then this output from the patch attention module is fused with the global features so that the classifier can detect whether this is a live fingerprint or a spoofed fingerprint. With this network, they have shown good results with most existing data sets on fingerprint identification, including the most recent one on live data 2017, where we have good accuracies. So mainly from this work, our main contributions are that we use both local patches and global features so that this is robust against cross sensors and cross data sets. The novel feature fusion strategy helped us a patch attention model, and we could achieve state-of-the-art results by combining both handcrafted features and deep semantic features extracted. For more details, please visit the poster at
motion between two images. We want to solve this with deep learning. The reason for that is deep learning allows us to learn good features for pixel matching. It also performs scene reasoning where it is difficult to do analytically. One of the key challenges of oblique flow estimation is the large motion. Standard CNNs only have small receptive field, which cannot cover this large motion. And the standard solution to that is we create a multi-resolution image representation and use warping to refine the estimation. This approach works as follows. First, we create an image pyramid of 2 images. Then we estimate the motion from the coarsest level to the finest level, and we use the warping for the motion compensation. There are 2 problems of this approach. First, it cannot cover situations where small things move fast. Second, warping will create some artifacts, which we will see later. Let's look at the first problem. At low resolution, small things disappear. And at high resolution, the motion is too large to be covered. Therefore, this pyramid-based approach will necessarily miss the situations where small things move fast. And what's the problem of warping? With ground truth oblique flow, if we warp the second image, we will see there's a doubling effect, that the dragon head appeared twice in the warp image. The reason for that is warping cannot deal with situations where occlusion happens. We provide mathematical analysis why this is the case. To solve the problems, we propose deformable coarse volume. The key idea is instead of deforming the images, we deform the correspondence. Therefore, we avoid artifacts created by downsampling and especially by warping. Based on this idea, we propose the Devon network. This network has several features. First, it estimates oblique flow in a single high resolution. It doesn't use warping, and it also has very small model size. Results show it is very effective in estimating the oblique flow where small things move fast. Thank you very much.
Today, it's my honor to present our work, Stochastic Dynamics for Video Infilling. The paper is a joint work of USC, Nanyang Technology University, and Columbia University. Our research focuses on a task named video infilling. Video interpolation can generate transitional frames between consecutive frames with similar content. Video infilling hallucinates the possible frame sequence in long-term intervals. The applications of video infilling includes reconstruction of surveillance camera with low frame rate, or missing frames restoration of vintage videos, live sports stream, or occlusion recovery. There are 3 challenges for our task. First, the inputs are sparse and discontinuous. Therefore, unlike video prediction, we cannot get initial momentum of the video sequence. Second, video infilling has to generate sequences that can smoothly transition to the end. The observation of the last frame becomes a long-term coherence requirement. Third, as shown in the image, long-term intervals that we need to generate possesses more uncertainty than shortened intervals. To model the dynamic under high uncertainty, our model uses reference module to first extract reference vectors from all observed frames. For each timestamp t, we infer the distribution p inference based on these reference vectors. Then, we sample the dynamic vector zt from the distribution. Finally, we use a decoder to generate the frame x tilde based on zt and previous generated frames. To train the model, we designed 2 kinds of losses. Pixel losses supervise the reconstruction quality of the generated frames. Dynamic losses make sure the inferred dynamic is close enough to the dynamic of the ground truth sequence. We compared our model with multiple state-of-the-art models on KTH, stochastic MNIST, via robotic arm, and UCF-101. Here shows the video result of KTH. We also filled the gap for long videos in UCF-101. The inputs are 1 reference frames in every 8 ground truth frames. Thank you for your attention. Please visit our poster at poster session 6.
Hello, I'm Anirban, and I'm going to present cross-conditioned recurrent networks for long-term synthesis of interperson human motion interactions on behalf of the authors who unfortunately couldn't make it to the conference. Motion generation is a highly stochastic process. This work explores long-term 3D motion generation for duet interactions. Zhu et al. Showed how autoregressive models can be leveraged for long-term motion generation. Martinez et al. Showed how the prediction errors can be minimized using residual connections. However, a direct extension of the single-person motion models to complex duet interactions delivers suboptimal results. This work leverages autoregressive and encoder-decoder recurrent architecture called CCRNN by interchangeably utilizing two separate fixed-length cross-person motion prediction models, PRNN and FRNN. The main idea is that the interperson correlations can be leveraged for motion generation. Aiming to impose a strong structural constraint on 3D pose estimation, a view-invariant generative latent representation is learned. CCRNN is trained under a collection of variable conditioning schemes with 4 phases. During the first phase, pose for person B from time step t+1 to 3t is predicted. These predictions are used under the second phase for prediction of person A from time step 2t+1 to 4t. Predicted A's from the second phase are used by the third phase for generating B's from time step 3t+1 to 5t. Finally, the fourth phase uses the predicted B's to generate A's from time step 4t+1 to 6t. These 4 phases are seeded by ground truth pose A from time step 1 to 2t and by pose B from time step 1 to t. A mean squared error loss is taken over each person's predicted pose. The prediction losses are weighted with an exponential decay rate. Coming to the results, the bar charts report prediction error on the 3 datasets for actions like dancing, hugging, kicking, etc. The proposed method performs better than other approaches on both short and long-term motion prediction tasks. Motion generation results are presented in this diagram. We can see that CCRNN generates valid long-term pose sequences unlike ACLSTM. Some more results on motion retrieval and critic-based pose sequence realism evaluation. CCRNN provides more realistic motion generation than the ACLSTM method. Finally, we can conclude that the interperson correlations can indeed drive long-term motion generation under a hierarchical autoregressive learning setting. Variable chaining in CCRNN improves the stochasticity of the model. More details can be found on the poster. Thank you.
Hello everyone, I'm Siddhant from IIIT Hyderabad, and I'm presenting this work for the authors from the Vision Intelligence Lab, MERL Jaipur, as they could not be here due to unforeseen circumstances. So this paper presents a unified deep framework for moving object recognition. The motivation behind this work is to develop a deep learning based framework to perform online moving object recognition in streaming videos. This is the first attempt for simultaneous localization and classification of moving objects in a video. The difference between object detection and moving object detection and MOR is depicted here. So we present the motion rec architecture here. We first estimate the background with the TDR module from T recent history frames. The estimated background, temporal median, and current frame are assimilated and forwarded through the resonate backbone to extract spatial and temporal dimension-aware features. Moreover, the base features from the current frame is also extracted to reinforce semantic context of the object instances for robust object classification. Afterwards, multi-level feature pyramids are generated from Mouse-Knight response. The dense boundary box and category scores are generated at each level of the pyramid, similar to the retina net model. Sample visual TDR responses at the intermediate stage on motion rec, we can see that the background is quite robustly estimated here. We show visualization at different pyramid levels which capture the salient motion features. The training and the testing data set description is presented in this table. The quantitative results and some baseline comparison are also shown in this table. We also conduct the speed and efficiency analysis of two different variants of the network. More details can be discussed in the poster session. Motion, MOR performance across intersection over union thresholds are depicted for different video sequences. The qualitative results of the proposed motion architecture is shown in the next two slides. Thank you, and please visit poster number 43 for more details.
Hi everyone, I'm Simon from Boston University, working with Huizhen and Casey and Co. Today I will introduce our work, two-stream and improving motion modeling in video generation. Generative models learn to model the distribution of the high-dimensional data. Recently, due to the appearance of some powerful deep learning methods, such as GANs and VAEs, it achieves great success in the image generation. However, when it comes to the video generation tasks, some recent works fail to generate convincing motion of videos in either synthetic setting or real ones. We relate this failure with their model architecture. Note that except that the video GAN incorporates a separate generator to solve the static background, both T-GAN and MoCo GAN still adopt a single generator to generate the content motion together. In this paper, we propose a model with two parallel generators to generate the content and motion separately, and design a fusion mechanism to merge the content and motion at several stages. Our model removes the disturbance of motion during content generation and produces action-relevant movement consistency in the sequence. We compare our model with MoCo GAN video VAE over 4 different data sets and use inception score, intra-entropy, and intra-entropy to quantitatively evaluate the generation. Here is our quantitative results. We can see our method outperforms the baselines and our variance over many matrices across different data sets. Here is our qualitative results. Our model is on the left, and while MoCo GAN is on the right. From here, we can still see our model produces better motion throughout the sequence. We conduct several ablation studies to show the disentanglement of content and motion happening in our model, and also to show the benefit of the multi-scale motion fusion and motion mask in the fusion mechanism. That's all for my talk today. Thank you for your attention. Please come to our poster for more details.
Hello everybody, I'm Matthias Inmann from the University of Erlangen in Germany, and I'd like to present our recent work on non-rigid multiview stereo. Yeah, multiview stereo is a common tool for RGB-based dense static 3D reconstruction, and it has some typical properties like wide baseline, unorganized data with temporal gaps, and it works very well for static scenes, as has, for example, been shown by CallMap. But many day-to-day scenes contain non-rigid motion, for example, faces. In these cases, static multiview stereo fails and the geometry and motion information is missing because the epipolar constraint is violated. Related work mostly tackles non-rigid structure from motion, which usually only reconstructs sparse points, or it utilizes other constraints such as dense video input, multi-camera input, depth data, or shape templates, or other constraints, as shown in these examples. Our method, however, is designed to work in a similar setting as static multiview stereo, so also white baseline images, no organized data, and so on. It works as follows. So from a set of input RGB images, we first select 2 images that contain minimal deformation to reconstruct an initial canonical point cloud. And then we use every other image and estimate the deformation and the depth per image using its camera pose, and then update the canonical point cloud to have in the end per image the deformation and the depth such that we can, for example, replay the deformation or interpolate in between the point clouds. I'd like to show some example results. So here we see the output of our dense photometric optimization of our deformation graph, which shows that the photometric error between source and target image is minimized. We conduct a thorough synthetic evaluation, which shows that we reduce the relative error and increase the completeness compared to other methods. And we conduct evaluation on real-world data on several data sets, where I'd like to show some animations now. So here we select the 2 images with minimal deformation and reconstruct an initial canonical surface. And now we use every other image and then estimate the deformation and the depth to complete the point cloud of this human being. And now we can replay the deformation and interpolate in between the time steps. And please note, all these reconstructions are just done by these 6 images. So here we see another example data sets. Also first the initial canonical point cloud and then the fulfilled point cloud. And also here we can interpolate in between the time steps to generate 4D animations. The final example shows a more stronger deformation where the globe really gets squeezed inside, and even that is able to be captured by just 6 images. Thank you for your attention, and please visit our poster.
Hello everyone, I Gaurav Singh present to you my paper Fusing Semantics and Motion State Detection for Robust Visual SLAM. Achieving robust pose tracking and mapping in highly dynamic environments is a major challenge faced by existing visual SLAM systems. We increase the robustness of existing visual SLAM by accurately removing moving objects from the scene so that they will not contribute to pose and map estimation. Our work highlights the importance of distinguishing between the motion states of objects. We integrate the moving feature removal into the existing SLAM frameworks. In order to retain the usual features, semantic information is fused with the motion state information. In the geometric clustering, first the scene flow is estimated using the feature matches. Then a graph is constructed and pruned. Finally, connected components are extracted. On the other hand, semantic labels of image are obtained using deep learning-based semantic segmentation. During the fusion task, both class and motion state information are fused via a probabilistic method utilizing distance transform, as shown in right bottom. The qualitative experiment shows that our proposed fusion approach overcomes the limitation of both geometric and semantic approaches of detection. As you can see, the geometric clustering does not capture the whole moving region because of sparse distribution, while semantics do not have motion state information, but the fusion considers both information and robustly identify majority of moving regions. The ablation study also reflects that the proposed fusion B plus G plus S has lower errors compared to geometric B plus G and semantics only B plus S in general. Further, the proposed method also outperforms other state-of-the-art methods on highly dynamic datasets such as TUM and Apollo datasets. The other detailed results can be seen in the poster. In conclusions, by removing majority of moving features, thus robustness of maximum consensus outlier removal scheme is enhanced. Our ablation study highlights the importance of distinguishing between the motion states of potential moving objects, which can be moving or may be static. To demonstrate the effectiveness of the proposed technique, experiments were conducted on challenging datasets TUM, Kitty, and Apollo, and the result shows that the proposed visual SLAM outperforms DS SLAM, Detect SLAM, DynaSLAM, and ORB SLAM. Thank you.
Hello everyone, my name is Ozan Tezcan. Today I will present about our recent work on background subtraction for unseen videos. Background subtraction is a binary image segmentation problem. So the idea is to classify each pixel as either foreground or background. And here you can see some examples. So the white pixels are foreground for these examples. And currently we categorize the state-of-the-art algorithms. And we categorize them into like 3 categories. The top performing ones are of course supervised algorithms. Those are generally like deep learning, CNN, or GAN-based algorithms. Then there are some post-processing and ensemble algorithms, which are combining several algorithms into a single algorithm. Then there are some unsupervised algorithms. Those are mainly like model-based traditional algorithms. Here, of course, like supervised algorithms are performing the best, but the gap is very huge between the supervised and the next category, which is kind of surprising because the data set is kind of small. There are only 50 videos. So we wanted to analyze it, and we saw a like very big bottleneck for the supervised learning algorithms. The thing is that they are mostly video optimized or video group optimized. And here what I mean is that they are using some frames of the same video for training, and like the remaining frames of the exactly same video for the testing. So their performance for the unseen videos is not evaluated. And when we try to take the like best performing algorithm and apply it in an unseen manner using a cross-validation, we saw a like very huge performance decrease, as you can see here in the table. And we think the main reason is that because they are mostly using just the current frame as their input, as you can see here. So there's a current frame, then there's like very deep network, then they are trying to do the background subtraction. But for example, in this case, whether the sofa is background or foreground, whether the box is foreground or background is not very clear. The network can memorize it for a single video, but it cannot like generalize it to the general case. And to overcome this, we think we need some temporal information. And we get this temporal information by some simple background models. Here we use 2 different background models from 2 different time scales. And we saw that this increased the performance like significantly. And then to further increase the performance, we also thought we can use some semantic informations because semantics are also kind of very important. For example, generally person are foreground and like walls are background. So this information might be useful to the network as well. And then this gives us our full network. We have some additional data augmentation as well. Yeah. So, and to compare it with the state-of-the-art algorithms, we saw that it outperforms all of the other algorithms for unseen videos. And here you can see the results. Also, we did some full ablation study for the effect of all channels. And you can see the ablation study on the poster session. Also, we have some like visual results, some qualitative results in the poster as well. Thank you so much.
Hello everyone, I am Karthike and today I'll be presenting our work on disentangling human dynamics for locomotion forecasting with noisy supervision. In this work, we define locomotion as the joint motion of several key points over the human body, and given the past history, we aim to predict its future. The problem has crucial applications in several autonomous driving scenarios, such as predicting motion of a jaywalking pedestrian. For example, in the scenario shown on the slide, the pose of the pedestrian determines if they want the car to wait, or a swift motion of a hand says to the driver that they want it to pass swiftly. Prior work focuses either on the problem of trajectory prediction or pose forecasting, each of which ignores either the local pose or the global motion. In this work, we aim to model both of the streams and predict them jointly. Starting from the raw video, we extract several noisy incomplete pose using off-the-shelf methods, which are then denoised using the post-completion module. The overall motion is then split into the global stream, i.e. the motion of the root of the kinematic tree, and the local stream, which are forecasted separately. Finally, these streams are merged for future predictions. The forecasting module for both the global and the local motion, encode the information in latent space where the forecasting is carried out before decoding them for final predictions. Now we will overview the local stream. The local prediction network is based on a quasi-RNN backbone which applies flexible temporal predictions in the latent space produced by the autoencoder. Now for the global prediction module. In this work, we present a novel egocentric trajectory prediction module that achieves a state-of-the-art performance utilizing several low-level vision signals such as pose, depth, and ego motion. In this work, quantitatively, our method achieves a state-of-the-art by outperforming several predicted baselines on JAR dataset. More results are presented in the paper. We perform extensive ablation studies to pinpoint the merits of our proposed model. As seen, pose completion helps improve performance of all the streams individually, while orthogonally, disentanglement of the global and the local streams boosts performance further. We also study how the performance of our model scales with time. We found that the longer we predict, the more is the delta between us and the best performing baseline. Here are some qualitative results of our method. The blue represents the past ground truth position given as motion history to the model, and green represents our predicted future. Here are some more results on a longer time horizon. Again, blue represents the past ground truth motion history given to the model, and green represents our predicted future. Thank you.
Hello everyone, today I'm presenting adapting GradCam for embedding networks. This work is done at Borealis AI with Jianhui Chen, Hossein Hajmir Sadeghi, and Greg Murray. I'm Lei Chen from Simon Fraser University. Our motivation is in that a convolutional neural network usually consists of many convolutional filters. And for example, in a bird embedding network, those convolutional filters may correspond to different parts of the birds. And if two birds get similar embeddings, it's likely that they activate a similar set of filters due to the similarity in their parts. Many works have been proposed for interpreting and visualizing a classification network, while relatively few are designed for embedding networks. In this work, we propose to adapt the GradCam for embedding network. First, we train an embedding network using the conventional triplet loss, which depends on training triplets that consists of an anchor image, a positive image of the same label, and a negative image of a different label. Once this network is trained, we send these triplets again to the network and backpropagate the triplet loss to the last convolutional layers and get the weights for different filters in this layer just as in GradCam. Once we have this filter weights together with the filter activations, we can generate a heat map indicating where this network is paying attention to when generating the embedding for this anchor image. We also use multiple triplets to reduce the randomness in the sampling process, and for each training triplets, we will also store its weights of different filters as well as embeddings for later use on the testing set. On the testing set, the previous approach cannot be directly applied due to the absence of the labels to form those triplets. But we cover motivation that images with similar embeddings are likely to activate the filters in a similar way. So for a testing image, we retrieve its nearest neighbor from the training sets and together with its weights of the filters, and we apply this weights directly on this testing image to generate its heat map. For experiments, we consider CUB200 datasets of 200 bird species, and we also consider a GTASO dataset of house satellite images. To quantitatively measure the visualizing of the embedding network, we consider a metric which is the mean ratio of the GradCam activations inside the ground truth bounding boxes or segmentation mask as the visual attention accuracy. At last, we show some qualitative results on the CUB200 datasets of visualizing of the training images and testing images with the just described weight transfer. Thank you, and please come to our poster for more details.
So, hello everyone, I'm presenting on behalf of Mahart from Data 61 Australia.
this work basically converts low resolution mosaic multispectral images to high quality multispectral images. Regarding the motivations for this work, snapshot mosaic images sensors are fast and portable devices. However, they have low spectral and spatial resolution, and their applications range from agricultural and astronomy. So obtaining high-quality RGB images from low-resolution multispectral images is crucial. This slide demonstrates how spatial resolution of multispectral camera. When multispectral pixel with 16 channels occupies the space equivalent to 4 Bayer pixels. In this slide depicts spectral constraints of our multispectral camera. It does not completely convert the blue and red bands and has narrowly and sparsely mapped spectrum. It's hard to generate RGB images using traditional methods, for example, interpolation plus color matching function. Some notes on previous work. In terms of super resolution, there are lots of work. Our work builds on RCAN network, which is the state of the art in super resolution. And in terms of color prediction, most of the methods work based on interpolation and using a color matching function. Hence, our methods here establishes the state of the art. Our first contribution is that we present mosaic images as zero-padded data cubes instead of conventional multispectral cubes. We also add a texture network module to the RCAN network. We use L1 loose light to point at the output of RCAN and at the output of TS-RCAN. For training, we used 250 registered image pairs, 25 for validation and 21 for testing. The results show that our method significantly outperforms traditional and state-of-art methods. Here are some results which compare the traditional methods with our method and the ground truth. If you have any questions, please come to the poster.